All right, that was Linda Ronstadt asking, "Are you still within the sound of my voice?" And yes, you are still within the sound of Mr. McMurray's voice. Sorry about that, but that's the way life goes sometimes. All right, we are going to talk about sound and what it means if you're still within sound distance of somebody. All right, and so let's talk about sound waves. We talked about sound waves a little bit before. They said they're compressional, which means that they're squeezing atoms together and then they're squeezing apart, spreading apart, and then squeezing together, spreading apart, and they're squeezing and spreading apart in the same direction that the wave is moving. It's moving that direction, and they're parallel to that, where they're squeezing together and spreading apart. Kind of like if you squeeze a slinky together. All right, if you remember, we talked about that a little bit last time, but a compressional wave would be like the top slinky, where you squeeze it together and then it spreads out and springs together, spreads out, springs together. Not like the transverse wave, which is the up and down one, which we'll talk about when we get to light. But compressional wave is more like that, the slinky being pushed together and spreading apart. Okay, now where they're squeezed together, we said, are called compressions. Where they're spread apart, they're called rarefactions because they're more rare or less atoms there, therefore they're apart. Okay, and we also talked a little bit about the speed. On sound, it goes fastest in solids. All right, so it actually will go fastest in solids. Then in liquids, it'll go a little slower. Air, slower, and it will not travel in a vacuum, which is when there is no, whoops, there should be one, there will be no sound in a vacuum. It has to have something to move through, unlike light and some other forms of transverse electromagnetic waves that we'll talk about later. Okay, and so that's kind of basically how it goes. It also depends on the temperature of the medium. All right, if you're going through warm air, it will move faster. All right, if it's going through cooler air, then it will move slower. Okay, now that doesn't mean that if I'm out on a cold winter's day and I talk, it will sound like that, because it's not that much slower, but it is a little bit slower, and it will cause it to bend or refract, kind of like we talked about under the wave part of the notes when it goes into different speeds. All right, now let's talk about the ear for just a second. You have a drawing that you need to label, and take a little bit of notes on it. All right, so real quickly on the ear drawing, which you should be getting today. First of all, the part we really think of the ear when we talk about the ear is really probably in some sense the least functional part, but it is still important, and that is the outer ear, the ear flap. All right, and that is called the external pinnae. Okay, and that's just this outside part of the ear that flops around. If you look at those, everybody's ear looks a little bit funny after a while, but anyhow, there we go. Now, its main job is to funnel in sounds that are coming out here, vibrations, and it funnels them into the ear. Okay, if you put your hand on the outside of your ear, you'll notice that everything sounds a little bit louder. Why? Because it's just making even a bigger funnel to help funnel those sound waves in. And so a lot of times people trying to hear will cup their hands. So the external pinnae funnels the sound waves into the ear. All right. Now, once it gets into the ear, we have the external auditory canal. All right, and basically it's just this tube, okay, or canal that carries the sound waves in. Now eventually it hits a little membrane across here, which is called the eardrum. All right, fancy name for that is the tympanic membrane. Tympanic has to do like drums, it vibrates, and so when the sound waves hit this, the vibrations hit it and cause it to vibrate. Now when it vibrates, it makes this first little bone here vibrate, which is called the hammer or the malleus. All right, similar to the word mallet that comes from. It vibrates and hits the next one, which is called the anvil, because blacksmiths used to use their hammers to bang on the anvil. It kind of looks like an anvil a little bit there. Anyhow, it's also known as the incus, I-N-C-U-S, but anvil will be fine for us. And then finally it hits this one here, which looks a lot like a stirrup. All right, or the official name is the stapes. Okay, and it also vibrates. Now, when it vibrates against a little window here that's filled with fluid, and this whole little tube thing here and these up here are filled with fluid, and this is called the cochlea. Okay, so when this vibrates, the stapes vibrates against this, it vibrates here, it vibrates these fluids. There are little tiny hairs in here that pick up those vibrations, and they send that information through an auditory nerve to the brain up here. Okay, and so the cochlea is where these vibrations are sent, and then it's sent to your brain, and then your brain processes those vibrations and stuff, and that's what you hear as sound. Okay, we're not going to these. These are semilunar canals, just for the record. These face in different directions, and these are what help you maintain your balance. If you spin around for a lot, it'll swish the stuff around in there so much that for a while you're kind of disoriented, and it takes a while. But these are the things that help you orient, whether you're up or down or upside down or sideways and whatever. This one down here we're not going to talk about right now, but this is your inner ear. This is the tube. When people get tubes in their ears, this is where they get those tubes put. This hooks down to your mouth so that the air pressure can equalize on both sides of your eardrum. If you got really high air pressure here, but you had low pressure on the inside, it would push in on your eardrum and hurt. Or the other way around, if you had high air pressure here and low air pressure out here, then it would also push out and hurt. Either way could burst your eardrum, and that could be serious. So this allows the air to equalize in both sides. When your ears pop, if you go up a mountain or possibly in an airplane, then that's what's happening. It's the air getting in there, and it pops. That means the air gets in there and it equalizes the pressure on both sides, and it hurts until you do that. Okay, and that's called the eustachian tube. All right, but for right now, that's not the main thing, since we're talking about how you actually hear. All right, so for the next section, we're going to talk some about the properties of sound, and some of this will kind of go back to what we've already talked about in the wave notes, but kind of brush on that. So the first thing, we want to talk about the idea of intensity, how intense a sound is, or when we hear that, we talk about that as the loudness of the sound. Okay, if you remember, we said that when these compressions, the closer together they are, and then the farther apart they spread, and then the closer together they are, and then the farther apart they spread, has to do with the amplitude. If you have a very strong vibration, it's going to squeeze them together, then they're going to bounce way apart, spread together, far apart, and so forth. All right, if they don't spread together very much, and they don't spread out very much, and then they don't spread together too much, then that's going to be less amplitude, and that's going to be a softer sound. So if I yell like that, that's going to be where they're very compressed, spread far apart, spread together, and so forth. But if I whisper, then they're just barely squeezing together, barely spreading apart. Okay, and so basically that has to do with the amplitude. Okay, now the amplitude, obviously, in some cases, in this case, has something to do with the amount of energy. The more I vibrate the air, then the louder or the more amplitude it's going to have. Okay, and the amount of energy that the wave carries is called the intensity. Okay, and that is, like I said, the amount of energy that the sound wave carries. All right, now how I hear that when it goes through the auditory canal, the eardrum, the three little bones, and eventually to my cochlea and then sent to my brain, basically that is what our brain interprets as loudness. Okay, so brain is basically how our ear or our brain registers intensity. Okay, the more intense it is, the louder it is. The more energy the wave carries, the louder we hear it as. Okay, so what we hear is loudness, but it's a measure of intensity or the amplitude of the sound wave. And basically, the more intensity a wave has, the farther it will carry. The louder a sound is, and the farther it will go. Because as it spreads out, it tends to lose the energy. Think of it as kind of like friction, and they don't compress as much, and they don't spread out as much. And so eventually, the sound gets fainter and fainter, and then eventually you can't hear it. Okay. Now, in order to measure how loud something is, all right, we measure that in decibels. All right, which is a symbol for that is little d, big B. Bells, named after Alexander Graham Bell. Deci All right, meaning 1/10. So actually, it's 1/10 of a bell. All right, which is the units that were named after Alexander Graham Bell, and so that is decibels. All right, decibels are the most common ones that we hear them measured in. Now we can hear anywhere from 0 decibels up to 120 decibels. Now you can't hear any lower than 0 because there's no decibels, then there's no vibrations. We can hear above 120, but this is the highest that you can safely hear. Anything above that is going to begin to destroy your ear and do damage to it and stuff like that. So loud noises, being on the front row at a rock concert right in front of a big speaker or something like that, those kind of noises, and jets and even a lot of lawnmower and equipment and so forth, if it's above that 120 decibels, can be harmful to your hearing. All right. Now, the next one we're talking about is the idea of pitch. And pitch, just like intensity was tied to loudness, pitch is tied to the frequency. Okay, pitch is high or low sounds. When we talk about high or low pitched, well, what does that? Okay, we talk to say if I'm on my harmonica, at one end of my harmonica I have fairly low pitch, at the other end fairly high pitch, which can be fairly irritating. Okay, so when we talk about how high or low pitched, that's what we're trying to talk about. Pitch then is how high or low sounding. If you're going through puberty, it may go back and forth, but that's okay. Generally, guys having to do with their vocal cords and the size of their Adam apples, and the vocal cords there tend to have lower pitched. Women in general have higher pitch. That's why the alto and soprano higher parts are women, bass and tenor are guys. But generally, it has to do with frequency. Okay, the frequency. Say we do this by lines instead of compression, and then they spread out, and then they're together, and then they spread out again. Okay, and then say we have one that has a higher frequency. They're squeezed together, spread apart, squeezed together, spread apart, spread apart, and then they're squeezed together. Well, this one has a higher frequency because there's more wavelengths going by in the same length of time. And so basically, the higher the frequency, the higher the pitch. Okay, so it's a direct relationship, and therefore then the lower the frequency, the lower the pitch. All right, so basically they're directly related. Now, once again, kind of like the other things, there are certain ranges that we can hear. Since we're measuring in frequency, that would be in hertz. Okay, we can hear, humans can hear from 20 hertz, which would be 20 wavelengths per second, up to about 20,000 hertz. Okay, and so we can hear within that range. Now that varies as you get older. You tend to lose some of the higher pitches. That's why they have the apps that can play the high pitched noises that your mom, dad, or the teacher may not get to hear, but it drives everybody else, all the kids in the room, crazy. So as you get older, you tend to lose the higher pitch. All right. Now anything above or greater than 20,000 are what we call ultrasonic. Okay, ultrasonic means we cannot hear that. However, like dog whistles and so forth, they can hear those higher ones. Ultrasound, we talk about ultrasounds that people look at babies and stuff like that. Those use ultrasonic pitches. Okay, now sonar, when they talk about sonar, using that for airplanes and stuff like that, that is also less than 20, so low that we can't hear it, are called infrasonic or subsonic. And we will take back up on that next time, but we will see you then.